This is 6.5 in Advanced Algebra 2 today. Today we're simplifying radicals, which is what we did last time. We simplified radicals, but everything came out just real pretty last time. Everything was either a perfect square underneath the square root symbol, everything was a perfect cube underneath the cube root symbol, and etc. Today, not so much. We're just going to kind of dive right in. You see number 1 right here. Notice the instructions. Do not use a calculator. This is hard enough to do at first with a calculator, let alone that we are asking you to do it without a calculator. So if you want to have your perfect note card out today, we can have it out if you want it. But realize that you won't get to use that on the test, okay? We need to kind of practice and get better. And some of the things that you've been hearing your math teacher say for the past few years of how your number sense is pretty shaky, you're going to find that out today if you don't have good number sense. So we want to simplify all of these radicals. For example, let me go back here. You've seen us simplifying the square root of 50, correct? We need to find the biggest perfect square that goes into 50 evenly. And remember, you don't get to use a calculator. The biggest perfect square that goes into 50 evenly is 25. How many times does it go in there? And that simplifies to be 5 square roots of 2. We're pretty comfortable with that. You've done that a few times, you know, and last year you did it, should have done it in Algebra 1. Showed you, if you wanted to simplify this, see that's the cube root of 16. You all realize that 16 is not a perfect cube. We want to find the biggest perfect cube that goes into 16 evenly. So that's why we've been asking you to know those numbers. Like if you was to make a list of perfect cubes, it'd be 1, 8, 27, and etc., correct? What's the biggest perfect cube that goes into 16 evenly? So we split it up into 2 radicals, and the trickiest part about this is you may understand it, but you put the wrong index up here sometimes. It's like, oh, you put square root symbols. You need to put cube root symbols, right? You got to put that correct index. Does an 8 go in there? How many times does it go in there? And we're going to have 2 sides today. This is the perfect side, because everything over here is perfect, right? We're doing cube roots. Is an 8 a perfect cube, correct? This over here I just call the non-perfect side. Sometimes I call it the scraggy side. It's not perfect. What is the cube root of 8, my friends? It is a 2. This cannot be simplified any further. And there's our final answer right there. So if we go to number 1, first question, what kind of root do you have? Number 1. Interesting. Some people do think that that's a 5th root. Is that 5 a coefficient, friends, or is it a little index? That's a coefficient, right? The little index, you can see how small they are? Like that's a cube root right there and all that, right above the little radical symbol. So on the little shelf, if you will. All we got to do is simplify that radical. So let's do it. We're going to go old school. We're going to split it up into 2 radicals. You're going to realize we want to do that. Find the biggest perfect square that goes into 54 evenly. And oh yeah, no calculator. Right. So get that done for me. You don't have a list in front of you. You don't have a calculator. You got to figure it out. 9. How many times does 9 go into 54? 6 times. You realize that the number on the left has to be a perfect whatever root you are here, a perfect square, correct? So now, the next thing we can do mentally, because you should know what the square root of 9 is. What's the square root of 9? Times 5, 15 square roots of 6. Are you with me on that? This guy, what kind of root? Let's split him up into 2 square root symbols. And I like to roll one concept at a time. There are constants in there, there are x's in there, there are y's in there also, correct? One thing at a time. 75. What's the biggest perfect square that goes into 75 evenly? 25. How many times? You see how I dealt with both parts? I did the perfect thing, and then I put the leftovers over there, right? 25, then 3. Now let's do it with the x's. Since this is a second root, you want to know, well, is this even a perfect square in the first place? Is this power a multiple of that index right there? So isn't x to the 4th itself a perfect square? The whole thing goes over here. All the x's are perfect. Cool? The y's. 7. 7 is not a multiple of 2, correct? So we need to just get as many y's as we possibly can. We need to work down to the next multiple of 2 from 7. Isn't that a 6, right? If you go lower than 7, isn't 6 the first number you come to? That's a multiple of 2. So we can put 6 y's over here. You with me on that? And how many y's go in the non-perfect side? Just 1. Is everyone down with that so far? Split it up is all I did. Cool? Now everything over here, woohoo, that's perfect, correct? Let's square root that. Doesn't that turn out to be 5x squared y cubed? Correct? Because the power over root trick, right? Where the exponents came from. Is everyone down with that? 4 divided by 2. You all right with that? Okay. And then this guy comes down. That's not perfect. Nothing's going on there. Groovy? Next one. What kind of root? Square root. Split them up. Find the biggest perfect square. That goes into 32 evenly. Doesn't 16 go in there evenly? And these are things you need to be practicing. We got to move a little fast today because of how many things we have to cover. But do you at least understand what I'm doing, right? And you might have to spend a little bit of time thinking these things through. And then x to the 8th. 8 is a multiple of 2, correct? That means the whole thing's perfect. That's all perfect over there. Rock and roll? So then this we will square root. 4x to the 4th square root of 2. Rock and roll? Why don't you pause the video and give number 4 a shot for me. So it's a square root. 12 gets split up with the 4 and the 3. C to the 6, that whole thing is a perfect square because 6 is a multiple of 2. D to the 3rd, not all of it is a perfect square. I can take 2 D's over here on the perfect side, correct? And there's 1 D left over there. Is that cool with us? Then 2C to the 3rd D times the square root of 3D. Righteous? Pretty simple so far. Feeling good? Next one. Watch the root. What kind of root is it? Cube root. Split it up into 2 cube root radicals first. Well, I guess I should really say this. You don't always have to split it up into 2 cube root radicals. First, you want to look at all the stuff underneath there and see if they're all perfect cubes or not. Is 27 a perfect cube? Is y to the 12th a perfect cube? Is 12 a multiple of 3? Yep. Is z to the 7th a perfect cube? Since there's not perfect cubes in every little guy right there, you need to split them up into 2 dudes, right? You said 27 is a perfect cube. That whole thing comes over here. You just told me that y to the 12th is a perfect cube. Doesn't that whole thing come over here? Z to the 7th, though, is not. How many z's can I put underneath my cube root guy, though? I need the next multiple of 3 less than 7, right? And isn't that a 6? So I can put 6 of them over here. And how many leftovers do I have? Just that 1 z over there, z to the 1st. And then just be careful. We're cube rooting now. So that would become 3 y to the 4th z to the 2nd times the cube root of z. Yes, sir, Bob? And make sure you cross your z's. Next guy, what kind of root? Cube. So that negative under there, who cares about him, right? It can happen, right, because it's an odd root. Is everything a perfect cube? Is negative 16 a perfect cube? So we need to split them up. What's the biggest perfect cube that goes into 16? 8. Bring the negative on the perfect side, though. Put the positive on the non-perfect side. So pull a negative 8 out. Variable-wise, I think we're pretty golden. A's, how many are you pulling on the perfect side? 3 of them. And that means there's how many left over here? 2. And then b to the 6th on the perfect side and b to the 1st on the non-perfect side. Does the split up make sense to you? Now it's cube root time. That'd be negative 2ab squared cube roots of 2a squared b. Now let's talk a little bit about how you know you simplified your variables completely. Like when it comes to the numbers, that's one thing. The variables, though, If you look over in the non-perfect side, on the non-perfect side, I want to say that one more time. On the non-perfect side, every one of these little exponents in here has to be less than that root right there. Is 2 less than 3? Is 1 less than 3? That's how you know you simplified it completely. For example, if this was a 4, don't you really realize that you have too many b's in this situation? You could have pulled an extra 3 of them out of there because there's 4 in there. You're looking for multiples of 3. So this guy always has to be less than the index on the non-perfect side. Cool? You see over here, they can be bigger than that because they're perfect, and you can actually cube root them. Sweet. Fourth root time. Do we need to even pull it apart? Is 32 a perfect fourth? Like I said, we're shaky at first. We don't know that note card as well as we think we do, right? Is 32 a perfect fourth? Nope. So we got to pull them apart. Don't forget your little indexes. Okay? Find the biggest perfect fourth that goes into 32. Like I said, if you got to look to your note card today, look to your note card. We need to practice and get better. $16, right? Isn't 16 a perfect fourth? And it goes in there twice. The variables we dominate now. How many a's you putting on the left side of the perfect guy? A to the 8. And then there's 1 left over here. And 20, can all 20 of them stay over on the left side? Because 20 is a multiple of 4, right? Good? Then, oops, we might get optical illusion because 16 is one of them crazy numbers. 16 is a perfect square, but we're not trying to square root. We're trying to fourth root. The fourth root of 16 is not 4. It's how much? 2. A to the second, b to the power over root. We need to divide 20 divided by 4, 8 divided by 4 situation. Then this guy comes down. Check your variable. Is the exponent on your variable less than the index in this situation? Yep. One more. One more. Why don't you pause the video, give him a shot. Got me some fourth roots. 16 is a perfect fourth. A to the 24th is a perfect fourth. And b to the 13th is not, but 12 of them can come over here, and doesn't 1b have to go over there? Right? Then all of this, 2, a to the 6th, b to the 3rd, fourth root of b. Boy, oh boy, oh boy. If only we could stop there, we'd have a pretty successful day. Seems like we understand what we're doing with that. Do I get a good vibe from you on this? Pretty basic. Fractions underneath the radical symbol. Can't have them. Pull them apart. Right? We got to pull them apart. First, I look underneath the radical before I do all this work. What kind of root are we taking? Square root. I want to see if everything under there is a perfect square. Is 36 a perfect square? Yep. Is 125 a perfect square? No. 125 is not. 225 is, but 125 is not. So I'm going to pull them apart. But I have a little bit of knowledge. When I pull it apart, I'm not going to write down square root of 36. What are you going to put in your numerator? 6 over the square root of 125. Cool? You could rationalize this right now. There's a problem. You can't have a radical in the denominator, right? We want to rationalize it. But I don't want to multiply by radical 125 over radical 125. It's like, this is non-calculator. I want to deal with as small as numbers as possible. Why don't we simplify the square root of 125 first? What's the biggest perfect square that goes into 125? So let's do this. Let me put this in a new window here so I got room to work to the right. Why don't we call it like so? That equals 6 over, you said 25, right? Goes in there 5 times. Isn't that really 6 over 5 square roots of 5? Right? Everyone see what I did? Simplified the square root of 125 into 5 square roots of 5. There's still a radical in the denominator, but what do you want to multiply by now to get rid of it? The number 1, right, is what we're multiplying by. That green number right there is 1, but it's radical 5 over radical 5. And that will make this turn out beautiful. And once we do this, I want to really explain to you what happens. Because most of you understand what to do, and you memorize the fact that radical 5 times radical 5 is 5, right? We're comfortable with that? We've done that for a couple of years now. So radical 5 times radical 5 is 5. But we've got to take it times another 5 down there. How much is really down there? And up top, you have 6 square roots of 5. That's our final answer. But like I said, I want to go above and beyond and really make sure you understand why radical 5 to the first times radical 5 to the first equals 5. Right? Isn't that what we just did? Check this out. That's what it equals. Isn't the concept, like if I ask you to take radical 2 times radical 3, don't you get radical 6 out of that situation? You multiply the radicands together, and 2 times 3 is 6. Isn't 5 to the first times 5 to the first 5 to the second? If I made it easier for you, radical x times radical x, isn't that radical x squared, right? Do you understand you add those exponents together? Isn't x times x, x squared? What does the square and this square root do to each other, my friends? They're inverses. They cancel each other out, and you're left with 5, correct? The square root of 5 times the square root of 5 is the square root of 5 squared, which is really 5. So just a couple more to beat it into you. Square root of 3 times the square root of 3 equals the square root of 3 squared, correct? And what does the square and the square root do to each other? Oh, they cancel each other out, correct? So watch this. Square root of x to the 5th, right? What would I need to multiply it by to turn it into a perfect square? X to the first, correct? Wouldn't I just need to take that times x to the first to make that a perfect square? Because that turns out to be this, right? Doesn't it turn out to be the square root of x to the 6th? And what is the square root of x to the 6th, my friend? It's x cubed, right? You see how I just trying to bump this up to become a perfect square? Yeah? So let's keep moving on. Oh my goodness. On the next page, before I try to split this thing up, I want to see if everything under there is a perfect whatever root we have. What root do we have? Square. Is everything underneath the radical a perfect square? So I got to split. Is everything in the numerator a perfect square? Nope. So I got to split up my numerator. So I'm going to have a radical over my denominator. That's not a perfect square either, right? So radical. I started with 4 radicals. 2 on top, 2 on bottom. Let's deal with the numerator. A's. 6 of them. Where are they going? Perfect side. All of them are perfect. Isn't a to the 6th the perfect square? B's. How many can we put on the perfect side? 2. And that means that there's 1 left over here. Are we good with that? Yeah? Find the perfect square that goes into 98 even. And that's where, like I was saying, some of us are just ahead of the game. We have numbers. Some of us have really good number sense. Some of us have been using the calculator your whole life, doing that, this, that, or the other. It's hard for some people to find the biggest perfect square that goes into 98, which is 49. How many times? And these are the things I'm asking you over the next few days to get better at. I took our non-calculator test yesterday, and it took me 10 minutes to do. 10 minutes. Because I know those things, left, right, up, down. That's my job. I don't think you'll get it done in 10 minutes. I feel if you get it done in 15 minutes, you're doing really good. Right? Take you a little longer. But just realize that you can't spend 30 minutes on that non-calculator test. You either know it or you don't know it because you have another test to take after that. You know what I'm saying? We gotta get quick at it too. So let's finish what we're doing here. Let's clean up all this perfect stuff. Doesn't this now become a to the 3rd, b to the 1st, square roots of b, over 7 square roots of 2. There is a problem with this answer. What is the problem with this answer? Radical in the denominator, right? So we have a what root in the denominator? Just hang with me. What root is in the denominator? Square root, right? So I'd like to multiply it by a square root over a square root. And what do I need to multiply this by to get it up to a perfect square? 2 to the first. Isn't 2 to the first times 2 to the first going to turn out to be 2 to the second? So we'll just multiply it by 2 to the first over itself. Which you're like, dude, we've been doing that for a couple years now. I gotcha. Right? Then upstairs, you're left with a cubed b. Then when you want to take radical b times radical 2, right, it all just goes underneath the radical. Which one would you put first? The 2. Over, what's radical 2 times radical 2, my friends? 2 times that 7? 14. Then just double check to see if anything can reduce, and nothing can reduce in that situation. Yes, sir, Rebob? Next one. Problem. Not everything's a perfect square. Right? X to the 6th is a perfect square. X to the 7th, excuse me, y to the 7th is not. So let's split it up. You want to square root x to the 6th right away? What is the square root of x to the 6th? It's not 3, it's what? X cubed or x to the 3rd, but just don't say 3, right? You with me on that? I know, yeah. And then is y to the 7th a perfect cube? So please split them up into 2 radicals. And 6 y's come over here, and 1 y goes over there. Right? And obviously, the left side, now we can clean up, is x cubed over y to the 3rd square roots of y. There's a radical in the denominator. What would you do to get rid of it? Y to the 1st, right? Radical y to the 1st. Radical y to the 1st over itself. And then right here, radical y times radical y is y times y to the 3rd, y to the 4th. Yeah? Be very careful with your handwriting. I have very bad handwriting, especially when I write on this inner right board. But watch where your exponents get located. Look at these 2 things. One of them says x times the cube root of y, and one of them says x cubed times the square root of y. Watch where that 3 goes, you know? Like just look how that 3 could very easily look like it's underneath that radicand situation right there. Cool? Next. That's where I know I feel your pain here on this Friday afternoon. What root are we taking? Cube root. We got to split them up also. Not everything in the numerator is a perfect cube, so I'm going to split him up into 2 cube radicals over another 2 cube root radicals, because 40 is not a perfect cube either. Yep. Numerator, get it all separated. And check it out with mine. Did you separate it correctly? Then, no calculator. Find me the biggest perfect cube that goes into 40 evenly without a calculator. And don't forget, you won't have that note card in front of you. You can look at it today. So if you had a list, which you do, isn't 81 too big? Right? Work backwards. Does 27 go into 40 evenly? 27 go into 40 evenly? Does 8 go into 40 evenly? How many times does 8 go into 40 evenly? 5 times. I can see the looks in some people's faces. They don't understand what I did. Didn't I have a cube root of 40 that needs to be split up? What's the biggest perfect cube that went into 40 evenly? It was 8. How many times does it go in there? 5 times. Correct? This now becomes p q cube roots of p squared over 2 cube roots of 5. Now here's where we need to really watch out. I have a radical in the denominator. It is what root? Cube root. This will not solve our problem. This doesn't work. You definitely need to multiply by a cube root over a cube root, but this just ain't going to do it. Because the cube root of 5 times the cube root of 5 is the cube root of 25. Right? Isn't 5 times 5 25? And last but checked, 25 is not a perfect cube. You with me on that? I have to get a perfect cube underneath here. So we made it much, much easier to understand after a little trial and error yesterday. Don't think of it as like, what number do I need to find? Isn't this 5 to the first? Right here, let me erase for a second. Smaller eraser. Isn't this a cube root of 5 to the first? You with me on that? Here's what I want it to turn out to be. I would really like it to turn out to be this. Because what does that cube in here and this cube root do to each other? Don't they cancel each other out? This is a 5 to the first power. 5 to the first times 5 to the blank equals 5 to the third. That's what I'm trying to figure out. What do I really need to put in this blank to make that a true statement? 5 to the second. Isn't 5 to the first times 5 to the second 5 to the third? So what I need to put underneath here is a 5 to the second. Now we're going to put that downstairs, but we're going to put a 5 to the second downstairs. We're going to put what 5 to the second actually is up here. What is 5 squared? 25. And here's what we got. We're going to show the long work. We're going to do it all for a couple. I know some of you see it already. You got it, right? Hang with me. But some of you don't see it. Now let's multiply this together. You got 2 cube roots of, what's 5 to the first times 5 to the second, my friends? It's 5 to the third. Is everyone with me on that? You got 2 cube roots of 5 to the third. Upstairs, you have a p and a q, and you've got a cube root of 25p squared. Is everyone cool with all of that stuff? But by God, something can clean up right here. What, oh what, is the cube root of 5 cubed? It's 5. Doesn't the cube and the cube root cancel each other out? It's 5. So this is a 5. You got to take it times 2, and what do you really have in your denominator down there? It's a 10. So let me show you, without the cool little trick, what it really turned out to be. It was really this. We wanted to take the cube root of 5 and take it times the cube root of something and get a perfect cube out of that situation. Well, we did this. We took 5 times 25, and we got 125. Right? Isn't 5 times 25 125? Look at your list of perfect cubes. Is 125 a perfect cube? Yeah, because it's 5 cubed, correct? Isn't 125 really 5 cubed? So extra examples here, right? Here's something with a cube root in the denominator. With me? I want to rationalize it. I got to multiply it by a cube root over a cube root. Isn't this 4 to the first, correct? What do I got to put right here to make it turn into a perfect cube? If this is 4 to the first, 4 to the second, which is really what number? What number is 4 to the second power? It's really a 16, right? That's the same thing over itself. Then you'd get this. You'd get 2 cube roots of 16 over, what's this turn out to be? What's that turn out to be? It turns out to be a 4 because it's the cube root of 4 cubed. You with me on that? It's the cube root of 4 cubed, and that really is a 4. Cool? And is it simplified? No, because the cube root of 16 can still simplify, but we'll just worry about that later. I'm trying to get you to understand a little bit of basics first. How about this? Cube root of 3, right? Isn't it 3 to the first? What would I need to multiply by right here to get it to turn into be a perfect cube? 3 to the second, which is really what number? 9. And that becomes 7 cube roots of 9 over, what does this turn out to be? It'll turn out to be 3. How about this right here? The 4th root of 3, right? I got to turn this into a perfect 4th. So what do I have to take this times right here? 3 to the 3rd, which is really 27, correct? I got to take it times the 27. What does this turn out to be? It turns out to be the 4th root of 3 to the 4th, which is how much? Turns out to be 3. And this is 4 4th roots of 27. Okay? So, I want to go back and kind of clean this one up. Did you see that this, doesn't 8 go into that evenly? And 8's a perfect cube? Here's why. See this number underneath here? He's really fancy. 4's a perfect square. Isn't 4 a perfect square? So could you write this as 2 squared instead? And then what would you really have to multiply this by instead? If it's a 2 squared and you're trying to get a 2 cubed out of the situation, what would you have to multiply this by? 2. Because really, isn't 4 times 2 8, and 8 a perfect cube in that situation? We'll get better. Trust me. It's a lot of information at first. We will get better. So let's try the next one, which, well, I don't know what that is. Oh, let's try this one. I made up one more example. See the problem? Do I have a radical in the denominator? Yeah? See this 7 right here? What do I need to multiply him by to turn him into a perfect cube? It's 7 to the first. What do I need to multiply him by? 7 to the second, which is how much? 49. See this x squared right here? What do I need to multiply him by to turn him into a perfect cube? X to the first, right? You with me on that? What's it all going to boil out to equal when you multiply? Well, this denominator is going to turn into this. Isn't it going to turn into that? Isn't everything underneath there a perfect cube? 7 to the first times 7 to the second is 7 to the third, right? X to the second times x to the first is x to the third. And what does the cube root and the third powers do to each other? They cancel each other out. And what did you get? All the bases back. You got nothing but the bases back, correct? 7 and an x. Weren't those the bases in the first place, correct? So just some tricks. Maybe, just maybe, you need to simplify a little bit after that, but at least you can rationalize the denominator that way. So let's try number.
So let's move here to 14 and 15, and I want to do 15 before I do 14. Got a problem here on 15. We've got a radical in the denominator, so we'll multiply it by, it's a cube root over a cube root. And then you got to start asking yourself, all right, is 3 a perfect cube? No. And is there any other, like, perfect numbers that go into it if you go to the next lesser root? Like, is 3 a perfect square? No, 3 is not a perfect square. So what you do is you think of this as 3 to the first, and I want to get it to be 3 to the third, right? So I need 2 more of these bad boys. And since I put a 3 to the third downstairs, upstairs I'm going to put the same thing, except we're going to call it a 9 this time. Or I said 3 to the third, I meant 3 squared. 3 squared is 9, right? So then when you multiply those together, here you'll get the cube root of 3 squared, which is just 3. Nothing but the base right there. You just get that base back. Upstairs you get 7 cube roots of 9. Remember, 9 is not a perfect cube, so that is the final answer right there. But when we jump back over here to 14, 14 is just a little bit different. So you do have a radical in the denominator, so you want to get rid of it by rationalizing. You'll do a cube root over a cube root. But 4 is like a special number. 4 is a perfect square. And you know, I know this is a cube root, but if you think down to the squares, you can think of 4 as 2 squared. because he's a perfect squared, and that's going to make this simpler to deal with, because now if I've got 2 to the second in this radical, I need a 2 to the first in this radical, because then I'd get 2 to the second times 2 to the first is going to give me that 2 cubed in that situation, and that perfect cube and cube root cancel each other out. So since I put a 2 to the first in this guy, I need to put whatever 2 to the first is upstairs, and that's going to give me a 2. And down here, again, remember, this is what you got. You had 2 squared times 2 to the first. Isn't it really the cube root of 2 cubed in that situation? Because you already had 2 base 2's in this guy. You just needed one more. So those, again, cancel each other out, and you got nothing but the base back on this bad boy. And upstairs, you got the 2 cube roots of 2 again. Then you got to check, see if that can simplify, and you get the 2 over the 2. So that really, those cancel each other out, and this is nothing but the cube root of 2. So all of that mess right there was really the cube root of 2. That's weird. Let's try some more of those. So here, you got yourself some radicals in the denominator, or I should say a radical in the denominator. Since he's cube root, we'll multiply by a cube root radical over itself. And let's think 3 is definitely not a perfect cube. Well, is 3 a perfect square or anything like that? No, 3 is not a perfect square, so this is really 3 to the first. I'm going to multiply by some base 3's. Well, how many more base 3's do I need to get up to this index number? You need 2 more. So, bingo. Now I'm going to put a 9 upstairs, because that's really what 3 squared is. And this is 4 cube roots of 9 all over nothing but the base 3. Then you check to see if that can reduce. Not happening, baby. Not happening. Down here, we got ourselves a problem again. We got a radical in the denominator. Nothing's perfect in there. There's no perfect cubes that go into 3 evenly, because if you had your list, you know, it's like 1, 8, and then 27. It's like 8's even too big. So like 7's not a perfect cube, and there's no perfect cube multiple. So we're going cube root of over cube root of. Let's go one at a time. 7, definitely not a perfect cube. But think back, is he a perfect square? No. So you've got 7 to the first. And here, when it comes to the base 7's, don't you need 2 more of them? Because you want to get a total of 3 of them, right? You've got 1 base 7 here. You need 2 more base 7's right there to clean that up. Here, x squared, this power is less than that root, so we're in good. We can't pull a perfect one out. But how many more x's do you need to get it up to 3 so it becomes a perfect cube? You need 1 more, right? So we got that 1 more. And then upstairs on here, we're going to take the green number and really call him 49, and then the x to the first is still the x to the first. And now, if I multiplied this all out, you know, which you can do, you'd get the cube root of 7x squared times, well, let's just put it in there, dude. Let's try this. If you multiplied it all out, you'd still have the cube root radical around it. 7 to the first times 7 to the second is 7 to the third. X to the second times x to the first is x to the third. Isn't everything a perfect cube in that situation? What do you get back? Cancel, cancel. Nothing but the base. Nothing but the base. We had base 7's, booyah. We had base x's, booyah. Upstairs, we have to take 5 times this numerator, so 5 cube roots of 49x. And none of that will simplify. So this is just better because it doesn't have a radical in the denominator anymore. So here, 4th roots. Notice that 9 is not a perfect 4th, or there is no perfect 4th multiple that goes in there. So we need to rationalize by a 4th root over a 4th root. And you got to notice that's something special about 9. 9, if you go back a root, is 9 a perfect cube? No, he's not. So you want to try that first. You want to always go down in order. So if you're doing a 4th root, 9's not a perfect 4th. Is 9 a perfect cube? Nope. But is 9 a perfect square? Yes. So I'm going to change him to be 3 squared. So now I've got my base 3's. And I already have 2 of them. I need a total of 4. So if I've got 2 base 3's here, I need to get 2 more in this situation. So I get 3 squared times 3 squared is 3 to the 4th. What number is really upstairs is whatever the heck this is. 9. And now what do I get down here? Nothing but the bases. The fourth root of 3 squared times the fourth root of 3 squared is the fourth root of 3 to the fourth, and boom, those cancel. Upstairs, 11 fourth roots of 9, baby. 9. So it's weird, but you want to try to see how you can write this at the lowest base possible. Since 9 was a perfect square, we wrote him as 3 squared. Whoops, I skipped one. Let's do this again. Let's split him up since he's got a fraction underneath there. So this is really the fourth root of 6, which that can't simplify, over the fourth root of 5x. And on your list of perfect fourths, like there is no perfect fourth that goes into 5 evenly, so you're just going to do a little, all right, I need to rationalize you. And go one nugget at a time. The 5. 5's not a perfect fourth, he's not a perfect cube, he's not a perfect square, he's not a perfect anything. So you've got a 5 to the first. I need to get how many more base 5s to get into this index number? 3 of them. X, I've got x to the first, so I need 3 more of those. And what will I put upstairs? Whatever the heck this is, 125, if my pen would work. And I'll put the x cubed up there also. And now to multiply those together, I got to take 6 times 5, so I can punch that in my calculator. 6 times 5 is, or 6 times 125 is 750, so the fourth root of 750, x cubed over nothing but the base, 5x, baby, 5x. We should probably check also if this 750 it has a perfect fourth multiple. So on your note card, you know, it's like these are the perfect fourths that you got right here, 256, 625. 625 does not go into that evenly. 256 is what 4 to the fourth is. That doesn't go in there evenly. 81 doesn't go in there evenly. And 16 doesn't go in there evenly. So that's as simplified as it's going to get right there. Couple more, baby. This guy, he's already split up for me, though, so this is the problem. I want to multiply by a square root over a square root. And notice here, when it comes to the variables, this root is bigger than that, this power is bigger than that root. You just got to knock it up to get to the next square root multiple. So since that index is a 2, you need to move it up to an even number. So don't you need b to the first in that? Like b to the fifth times b to the first is b to the sixth, right? So doing a b up here also. And let's see what I get here. Erase those extra equal signs. I'd get the square root of multiplying those together, a to the ninth b over. This is really the square root of b to the sixth, so you have b cubed in that situation because you got to do power over root. And a lot of people would call that finished. He's not finished though, because if you look upstairs, you're never allowed to have a radical where the power in there is bigger than the radical. So we got to split that up like we did at the beginning of the worksheet. You got your perfect square roots over here, you got your scraggies over there, and you got a b cubed down here. How many a's could you actually pull out of this? Well, an even amount since that, so you can pull 8 of them out. You'd have 1 left over. And then you've got a b. There's nothing perfect about him. This power is less than that root, so he's golden. And the square root of a to the eighth is really a to the fourth, right? Power over root. And the radical ab is still there over b cubed. And now if you look at this, this is our final answer. You don't have a radical in the denominator, and every exponent on the variables here is less than that root number, which is a 2 in this case. Yummy! This guy here, cube roots in the denominator, so no bueno. And I want to see if I can clean him up a little bit. So 49, he's a special number. He's like 7 squared, baby. So I can change this into base 7s and already have 2 base 7s underneath that radical. I need 1 more, right? Because I have 2, I need 1 more to get a total of 3. X's, I only have 1, so I need 2 more in that situation. So what do I got here? Whatever 7 to the first is, which is 7, and x squared. And I've got 2 cube roots of 7x squared over nothing but the base 7x, right? Because you'll get a 7 cubed out of that, you'll get an x cubed out of that, and you're cube rooting. Check to see if you can reduce. Cannot reduce. Another one here. Split them up. Fifth root of 3 over fifth root of 4y. Got a radical in the denominator. So this guy upstairs can't simplify. 3 isn't a perfect fifth. So I'm going to do a fifth root over a fifth root. And this number right here, he's not a perfect fifth. He's not a perfect fourth. He's not a perfect cube, but he is a perfect square. So I can change him down to base 2's. And I have 2 base 2's in here already. I need a total of 5. So don't I need 3 more out of that situation? Here, well, I got 1y. I need a total of 5, so I need 4 more. What am I putting upstairs? 8, because that's what 2 cubed is, y to the 4th. And multiplying those radicals together, you'll get the fifth root of 8 times 3 is 24, and then it'll have a y to the 4th up there. Here, nothing but the base, 2y out of that situation. And on your fifth roots, 24 can't simplify because it goes 1, and then the next fifth root is the perfect fifth is 32, so there is no multiple that goes in there. So here, very similarly, split them up. Fifth root of 8x cubed. Got a radical in the denominator, so I'm going to rationalize him. And this number here, 8, not a perfect fifth, not a perfect fourth, it is a perfect cube. That's what 2 cubed is. 2 cubed is that. So I have 3 base 2's. I need a total of 5, so I need 2 more. And x's, I have 3 already. I need a total of 5, so I need 2 more. And that would really be 4x squared is what you really got in there. And what you have down here, nothing but the base. And up here, fifth root of 3 times 4 is 12x squared, baby. Winner, winner, chicken dinner. And the last one here, fifth root of 32 over the fifth root of 27y. Upstairs, this fifth root of 32 is really 2. Right, so I'm just going to call that 2 real quick. And I need to multiply by a fifth root over a fifth root. And 27, he's very special. He's not a perfect fifth. He's not a perfect fourth, but he is a perfect cube. That's what 3 cubed is. So I can change him into base 3's. Now I only need 2 more of those puppies. And I need 4 more y's. So that's 9y to the 4th. And when I multiply those together, remember I turned this guy into a 2. So that's really 2 fifth roots of 9y to the 4th over nothing but the base is 3y, baby. Let us know if you have any questions. Have a good one.